Okay, so in the last question of the problem, we are we are giving you one possibility to benefit from this heat output at condenser level. We can pass a flow rate of cold water, and this cold water will be heated from 15 degrees to 35 degrees. Okay, the question is what should be the mass flow rate of water in order to be able to extract heat from the condenser. Now look here, we can play with parameters. And sometimes, let's say, you need a higher output temperature for the cold water. You want to heat, for example, water up to 50 degrees, let's say. So you need to pass by a smaller flow rate. Okay. So here you can investigate, depending on your needs, what is the flow rate of water that you need and what is the temperature to reach. You can investigate what is the mass flow rate I can heat to a certain temperature. And sometimes maybe, let's say, if you need to reach high temperatures of 70 or 100 degrees, you might not be able to use this cycle because maybe the mass flow rate will be really very small. So it depends on the applications that you have. If you just want to use water for swimming pools, 35 degrees is great. If you just reach 35, it's fine. But if you need to supply water for shower, you need a higher temperature to kill bacteria. Okay, so you need to select appropriate cycles. Then maybe you need to look at cycles with higher pressure, and because for this case you can have larger values of Q dot out, which will give you larger mass flow rates as you desire. Okay, so to decide what application to use, it depends on the cycles that you have. For this cycle, you calculated Q dot out. So you determine what is the mass flow rate that you need of water, and you can find what is the maximum temperature I can heat to, and based on your calculation, you decide for what application you can use this water. If it's good for swimming pools, if it's good for domestic hot water needs, if it's good for underfloor heating, etc. Okay, so for example here, let us see the mass flow rate that will, if we need to reach a temperature of 35 degrees, what mass flow rate should be circulated in the condenser? It's really simple. We need to take energy balance for the condenser. So this is our condenser, okay? Our condenser, if we take the whole control volume, we have two paths. We have the path of the fluid in the Rankine cycle, and we have water, okay? So now if we enclose the whole condenser as control volume, please pay attention for the difference between taking the whole condenser and taking just the stream of fluid in Rankine cycle. Before, when I asked you to get Q dot out, we did the following. So this is our condenser. Okay, and we have two flows over this condenser. The first one is for our fluid of Rankine cycle. So the refrigerant that we are using for Rankine cycle, let's say here, I think they said steam. Okay, so it's also water, but at larger temperatures. Okay, so the working fluid is water also. Okay, because we have steam. But this steam is at high pressure and temperature conditions. Okay, so we have calculated the enthalpy, and we know all properties. Okay, so we know at the inlet of our condenser, the inlet of our condenser is 0.2, and the outlet of our condenser is 0.3. And we have already calculated H2. We know H2 and we know H3. Okay, that's why first, to get Q dot out, we didn't consider the whole condenser as system. We just considered as control volume, a control volume just enclosing the fluid of the basic Rankine cycle. Okay, so if we take only the fluid of the basic Rankine cycle, we can consider that we have it will lose heat to the outer environment. Okay, and when we do energy balance for this stream of fluid, we can say that Q dot out is m dot of steam, okay, times H2 minus H3, okay? Now, since we're interested in the other pass, because we need to consider now cooling water, okay? We have two approach here for cooling water. Or we take also cooling water alone, yani we say that we have here the inlet, Tn, okay? And we have, this is the outlet, T out. And the inlet and outlet temperatures are given, okay? And we need to compute the mass flow rate of cooling water, m dot cooling water. So to determine it, we have to approach. The first one is to say, if we neglect any loss, from the condenser, what is lost by the steam of the Rankine cycle is gained by cooling water. So this is a simple energy balance. Heat lost by this fluid will be gained by the other fluid, because we consider that our condenser is well insulated, so no heat losses to the outer environment. Okay, so you can say that this is Q dot gained by cooling water. Q dot gain for cooling water. Okay, and how you can express the heat gained by cooling water? We know that whenever we have a liquid, okay, you have here compressed liquid. It's you don't have vapor. Okay, you can write then that Q dot water is m dot of cooling water times, if you remember the sensible heat equation. What was the sensible heat equation? M dot Cp, specific heat of water, times mass flow rate of water times delta T. And here, because it's a gain, so we do T out minus Tn. Okay. So in this equation, the only unknown is m dot cooling water. So we can calculate the value of m dot cooling water. This is the first approach. Another approach is the following, is to say, let me consider the whole condenser. If I take the whole condenser as my, or the heat exchanger, the whole heat exchanger as my system, there is no loss to the outer environment. Okay, so no loss of heat, no Q dot, no W dot. Okay, so all you have to say is that I should consider the energy at inlets. So sum of energy flux at inlets equal to sum of energy flux at outlets. Okay, so if you want sum of m dot n energy n equals to sum of m dot out energy out. Okay, here you know that because it's an open cycle, we consider the work, when we include the work of pressure forces, you can consider, instead of E, you put enthalpies. Okay, so sum of m dot n Hn equals sum of m dot out H out. Okay, and you have that neglecting variation, of course, neglecting variation in potential and kinetic energies. And for a liquid, you know that enthalpy can be computed as Cp times temperature. Okay, so you can write now that what are your inlets? You have two inlets here. You have 0.2 as inlet for the fluid circulating in the Rankine cycle, and you have another inlet for water. Okay, so you can write first m dot of steam, which is the mass flow rate in Rankine cycle, times H2, plus second inlet is for water, so plus m dot of cooling water And we said that the enthalpy of cooling water is Cp times temperature. So Cp times Tn is equal to now sum of m dot out h out. So you have m dot steam times h out, which is h3, plus for the water outlet, plus m dot cooling water times T out. Okay. And if you rearrange your terms, you will get exactly the same relation as before. Okay. Which is that if you want heat lost by the fluid here will be gained by the other fluid. Okay. Question on this? Any question on this? Okay. Now, as we discussed together, we need to improve the performance of the basic cycle. So now we'll discuss several strategies in order to improve the performance of our basic Rankine cycle. Uh, as we said, one of the main limitation is the quality at the exit of the turbine. So we need to try to have a higher quality for point 2. So we need to shift 2 towards the right. And in order to do so, one technique is to not exit the boiler as saturated vapor, is to do what we call superheating. Yani we do extra heating in the boiler to reach the superheating region. And in this way, more you do superheating, you will have, when you go through the turbine, you will have a higher quality. Okay, so you can move up to this point if you want, up to saturated vapor. But here also we have a challenge, which is the more you do superheating, you have larger and larger temperatures. And you know that there is a limit for depending on the material of your turbine. So each material has certain constraints. It can sustain a certain maximum temperature. So depending on the material of the turbine, you are restricted by a certain temperature that you cannot exceed. If you exceed this temperature, you can deteriorate the material of your turbine and it will not work properly. Okay, so here we should pay attention for what is the limit, what is the maximum temperature allowable. This will limit, if you want, the maximum quality at the exit of the turbine. Okay, now if this quality is still not acceptable, and because we are not able to exceed a certain temperature, we can go to other strategies. So one first strategy is superheating. If it works well, it's fine. So we can heat until the limit, and if the quality obtained is satisfying, we can use this strategy. Okay, but in case the quality obtained is not acceptable, we can come up with another strategy, which is reheat. What is the idea of reheat? So in reheating, we don't want to exceed a certain temperature. We have a limit on the temperature, but still we need to reach higher values of quality at the exit of the turbine. That's why what we can do here, we can use what we call a multi-stage turbine with reheating process. What do we mean by this? Let us explore the following cycle. First, for this cycle, the components are exactly the same components of the basic Rankine cycle. The only difference is that when you enter your boiler, you don't exit it as, you do the design to not exit it as saturated vapor, but you need to heat more. Okay, so you continue heating until reaching the desired temperature, and then you enter your turbine. But as components, you are with the same components of your basic Rankine cycle. However, if you want to use reheat process, you need to do some modifications to your cycle. What is the idea of reheat? If you want to apply reheat techniques, okay, the idea is the following. First, in your turbine, you will have several stages. instead of one stage turbine, you will expand your fluid in two stages. So you have more than two pressures. Okay. So in this case, you need to work. You need to work with three pressures: P low, P high, and P intermediate. Okay. So you need to come up. You need to work now with higher boiler pressures. Okay. So the upper limit of pressure, you increase it. In this case, what will happen? So first, you work in your boiler at high pressure. You heat your fluid, and then you reach the superheated region until T. You don't exceed the limit of temperature. You stop depending on the temperature limit. But this is not enough for you because X is still relatively small. You need higher values of X, which is the quality of your steam. Okay. Then, since you are limited by this constraint, you cannot exceed this temperature, you do the following. You say, let me now stop here. I don't heat anymore. And I take my fluid, okay, to a first stage turbine. This first stage turbine will expand my fluid from high pressure to intermediate pressure. So I will just do, if you want, not a complete expansion, because a complete expansion will give me a quality X4 prime that is maybe not satisfying. Let's say, for example, it's 0.7. So I have 30% of liquid droplets, which is not good for my turbine blades. I put a minimum quality. Let's say I need it minimum to be 90% or 95%, for example. Okay. So I say I cannot expand until low pressure. Let me expand first until an intermediate pressure. And of course, I design this. We do like optimization study. We try to study several possible intermediate pressure in order to decide on the best one to work with. Okay. So after some trial and errors, we can select a certain convenient intermediate pressure. And we say that we have a first expansion. Now, since I want to enter I want to enter now another stage of turbine. But before entering it, I need to increase the temperature again. Because if I don't reheat, okay, if I don't reheat, what will happen? I will exit at 0.4 prime, and I don't want this. So what I want to do, I want to heat again my fluid to reach, if you want, uh, larger values of entropy. Because when I increase my entropy S, I can reach then points with larger quality. Okay, because look, if you compare S2 to S3, S2 is smaller than S3. So now when you do the heating process again, you elevate your temperature, but also you elevate your entropy. Okay. And then, since in the second stage turbine also you have a isentropic process, but now you are working with a higher value of S, so you end up with a quality at number 4 that is larger than quality at 4 prime. And you can do reheating if you want, just to reach this temperature. You can reach the limit temperature in order to have higher and higher quality at the exit of the turbine. Okay, so your only limit here is the temperature. You can reheat until reaching the desired, if you want, temperature, which will give you the desired quality at the exit of your turbine. So this is called the reheat process. All we have to do is at the exit of the first stage turbine, which is called high pressure turbine, I take the fluid again to the boiler to be heated. And here you should pay attention. When you calculate your thermal efficiency, you should consider that heat is supplied at 2 stages. So when you want to calculate Q dot N in this cycle, you need to divide it into 2 parts. We can call them Q dot N1, which is, if you want, a heating process between 0.6 and 1. And also, you need to consider the reheating process. So you should add to this Q dot N at stage 2. Okay. And now you can pass your fluid through the low pressure turbine, okay, in order to expand to the desired quality at the exit of the turbine. In this way, first you were able to increase the quality, plus you didn't exceed your limit temperature. So if you want, you are restricted by two conditions here: maximum temperature to not exceed in order to avoid destruction of material properties, plus at the same time you have high quality to avoid any corrosion of your blades. So you are meeting requirement of metallurgical temperature limits, plus also you are avoiding any corrosion. So this design helped you to overcome all the disadvantages faced before. Okay. Now, to practice on this, I want you to try to solve this problem. Okay, I already posted for you this folder. The name of this folder is Applications of Thermodynamics to ENST. It's already posted in the revision material on Moodle. So please try to solve this problem, and we'll continue together. We'll correct it together, and we will continue with some important application that will enhance the efficiency of our power plant systems. Okay. Any question before we stop? Thank you. Bye bye.